Hey there, AP Calculus BC, and welcome to your second to last video of new content. We'll have a couple videos for our next unit, which is AP Review, but really there's only 2 new days left of learning. Today's lesson is meant to actually cover 2 class days, 86 and 87. 2 class days not because this is a crazy long topic, but just because I included a bunch of practice and really the repetition is going to help it sink in. So actually this technique is very, very easy, and you've kind of already know how to do it. It's just an extension of things you know how to do. So hopefully you enjoy our topic for today, Euler's method. Now, Euler is probably the most mispronounced name in mathematics. Yes, I know it looks like Euler. It is pronounced Euler, like oil with an ER at the end. Leonhard Euler was a Swiss mathematician. He did a lot with mathematics, but what we're going to use today is yet another way to approximate a value when we don't have an original function. And actually, I'm going to show you a really cool free response in a few minutes that I think does a great job illustrating all the different ways we've learned at this point of how to approximate a value without a function. So, what are we going to do? Well, Euler's method essentially gives us a way to find the general shape of a graph using tangent lines. It's all about tangent lines. And we're going to be able to do that without actually finding the equation for the graph. Now, Euler's method can be used as many times as you would like, but the more times you use it and the further you go, the less accurate it's going to be. So how does it work? Well, you need at least one point on the original curve. And I have the original curve done in blue on the screen over here. So maybe I can call this f of x if you'd like. Okay. So the original point that's going to be given to us is this point a sub 0. And from here, our goal is to figure out if we think that this is maybe, the 0th point, the first point, second point, third point, fourth point over here. They should probably be equal steps, so a little awkward. There we go. Our goal is to figure out what is this value, and maybe we should call it just f of 4, right? We're given f of 0, that's right here. We want to know what is the value of f of 4. But you're going to have to think that we didn't have the rest of this graph. We just had the actual starting point. So how, oh how, do I find an approximation for f of 4? Well, one way that we've done in the past is you could create a tangent line. You'd create a tangent line right at this point that we're calling a sub 0. Right? And our tangent line here is found by doing f prime of a sub 0 minus x minus times x minus a sub 0 plus f of a sub 0. And what that would do is it create a tangent line that looks something like this. And that's all fine and dandy, but if you wanted to find an approximation for this point and you used the tangent line that's way up here, this y value is not very close to the one we actually want to find. So although it is an approximation, it's not a super close approximation. So can we do better? And Euler says yes. What Euler's method does is it takes the total distance that you want to go from the point you know to the point you're trying to determine, and it splits it into smaller subintervals. I would say, just from looking through the last maybe 20 years or so of AP exams, it's common that they'll only split that into 2 subintervals. However, the first one we're going to do will be 3 subintervals, and I've never seen it go beyond that. Now, what do we actually do? Well, we're going to create a tangent line, as mentioned before, like so. And then, based on the number of subintervals, we're going to say, okay, this point might be a bad approximation, but if we stay close to the point of tangency, maybe this point right here, this is a pretty good approximation to our actual function. They're not very far apart. So, what are we going to do? Well, we're going to approximate this value, f of 1, using my tangent line. And what that's going to do is it's going to create a new value for us. How do we do it? We use our initial tangent line. I called it t sub 0, my 0th tangent line. You could do t sub 1, your first tangent line, whatever sounds good to you. And that's going to give us an output. It's going to find an actual, pun intended, tangible value where we can now say, okay, even though we don't know f of 1, we know that this value is pretty close. And then once we're there, what do? We just start the process again. So now what we're going to do is we're going to say, okay, now we know a new point. This new point is the point right here, a sub 1. And even though it isn't on the blue graph, we're going to pretend like it is, and we'll write a second tangent line. And our second tangent line, I'll do this in one purple or fuchsia or whatever color that is going to say, okay, we'll use this point, so it's going to pass through here, right? That's going to be the point right here, a sub 1. But we're going to do a new slope. Now, this slope is still based off of the blue graph. And how do we know all the slopes on this blue graph? Well, this is calculus. We're going to be given y prime, or a differential equation, or a way to determine the slope of the blue graph. So if I had the actual point f of 1, my tangent line would kind of bounce off the graph there. I don't have that, but I do have the same slope, so I can at least go parallel to that. And then I now have a line that's traveling in approximately the same slope, or the same rate, I guess, as the original graph. And now, guess what we're going to do? We're going to do another tangent line. So we're going to take the next point on my subinterval, plug it into our new tangent line, and use that to approximate f of 2. And then start the process again. So next we're going to go ahead and do another tangent line that goes right here. I'm trying to find a color I haven't used yet. Green seems good. And we're going to draw another tangent line using our slope formula, and it's going to look something like this. And if we connect all those individual pieces, all those different tangent lines, you'll notice that we don't get very far away from the actual function. And in fact, the smaller the subinterval, the more accurate you're going to be. And so we creep around, and now instead of using one tangent line that's really far away from the actual value, instead we just use multiple tangent lines, and once we get to the point we're trying to find, we substitute that into our latest tangent line and find an approximation. So you continue the process until you reach the point that's desired. The example to the right creates, well, 1, 2, 3, 4 different tangent lines to eventually approximate the value of, I'm going to call this f of 4. That's really it. You just write a bunch of tangent lines, the end. So how does this work? Well, we're going to look at an example and see if we can figure this out. We have a differential equation which tells us the slope of whatever the original graph of y is. Let y equals f of x be the particular solution. So this is the function, like this blue one up here. I should stay color coordinated, I think. Be the particular solution, and we know something about the particular solution. It passes through the point 0, 1. So this would be like our point 0, 1 in this case. Use Euler's method with 3 steps of equal size to approximate f of 3. Okay, well, I see 3 steps, so I'm going to go ahead and split this into 3 pieces, and we're going to start with our first step. Okay, so our first step is going to be our initial tangent line, and you can call it t sub 1 if you want to think of it, t sub 0, whatever sounds good. We need to differentiate between the tangent lines, though, so we don't think we're just doing t of something every time. So I'm just going to do my initial tangent line is found by doing what? Well, the initial tangent line, I should have written the point at the top, is going to pass through the point 0, 1. Okay? We have another tangent line and yet another tangent line, and we can even fill in the steps right away. It says 3 steps of equal size to approximate f of 3. So some people draw a quick little graph just to verify. We're starting at 0, we're getting to 3, we're splitting this into 3 subintervals. You can think of this as like our delta x. 3 minus 0 divided by 3 is 1, so each interval is 1. So we're starting at 0, 1, we'll write a tangent line there. Then we get to 1 comma something, I don't know that point, we'll write a tangent line there. We get to 2 comma something, we'll write a tangent line there. So let's name these tangent lines. Initial tangent line, t sub 0, I'll have to write a new tangent line over here, and I'll have to write another tangent line over here, and at the very, very end, we're going to say f of 3 will be approximated by this tangent line that I've written here at 3. Okay, so here we go. Initial tangent line, we need to use our derivative. So this is going to be y prime of what? Well, it looks like my y prime equation takes both an x and a y, so 0, 1 times x minus 0 plus 1. Y prime of 0, 1 needs to be substituted in here. You can show that step. I will in the middle, just so everything is clear. So I'll do this one in yellow. So y prime of 0, 1 is 2 minus 0 minus 2 times 1, which is 2, and 2 minus 2 is 0. Great. So my initial tangent line is 0 times x minus 0 plus 1, which if you distribute the 0 is just 1. That's easy. Great. Now what? Well, now I need to write a new tangent line. My new tangent line, and again trying to give you a picture of what's happening here, we have the point 0, 1, and I just wrote a tangent line. In fact, the tangent line is just the horizontal line, and it looks, we'll just do it in yellow, it looks something like this. And it says, cool, now that we have a tangent line, we need to write a new tangent line through the point at 1. Okay, well, how do we do that? Well, my new tangent line will be found by doing y prime of 1 comma something, right? It's at this point of 1 right here, times x minus 1 plus something. Well, how do we find the output? The output is found by using the previous tangent line. It's the output of the yellow line that's there. So it's going to be t sub 0 of 1. All right, so I guess we should probably use this tangent line over here, shouldn't we? Let's find t sub 0 of 1. I think the output is always 1, so that's easy. This is the point 1, 1. All right, so then that means my slope is also found by using 1, 1, and we have an output. So how do we find 1, 1? Well, it's 2 minus 1 minus 2. 2 minus 2 is 0, minus 1 is negative 1. And now we have our new tangent line. The new slope, negative 1, x minus 1, and the output is 1. All right, let's move on to our last tangent line. So now what we've done is we had a tangent line here, and now we have a new tangent line from the point 1, 1, which is going in a downwards direction. And so now we're going to build a third tangent line from 2. And so to build our third tangent line, we need a slope. The slope is at 2 comma something times x minus 2 this time plus, well, how do I find the y value? The y value is found by using the previous tangent line. The previous tangent line brings us somewhere close to the graph, so t sub 1 of 2. We should probably find t sub 1 of 2. Negative 1, 2 minus 1 plus 1, 1, negative 1 plus 1 is 0. 2 comma 0 is what we're dealing with here. Y prime of 2 comma 0, use that same equation, is going to be 2 minus 2 squared is 4 minus 0, so that's negative 2 this time. So my last tangent line is negative 2, x minus 2 plus 0. Whew. All right, so this last tangent line is even steeper and goes down something like this. All right, are we done? No, because we need to use this last tangent line, which reaches us to 3, to find the approximation for f of 3. F of 3 will be approximated by this tangent line, which means we just need to do negative 2 times 3 minus 2. Negative 2 times 1 is negative 2. And we have our approximation. So, long story short, 3 steps means 3 tangent lines. Write each tangent line using the previous tangent line to find your y values. The end. That is all there is to Euler's method, and it's not even presented in very creative ways. It's very straightforward. It's use Euler's method, here's the number of steps, go. The only way you're going to get better at it is, of course, by practicing. So I do have a bunch of free responses here, and that's why this is going to take a couple days. There is no free response that I've ever found that just has you do Euler's method all the way through. What I have found is that Euler's method is tested approximately one time on an AP exam pretty consistently, and it's either one multiple choice problem or one part of a free response. So as we go through these, let's make sure we can identify Euler's method, and then we'll go back and work maybe one or two and call it good. Use Euler's method. Awesome. 2 steps. Second free response, use Euler's method. 2 steps. Moving through again. Oh, hey, look. Use Euler's method with a step of 1 this time to do something there. We should probably do that one together for sure. Use Euler's method. Step 2 steps of equal size. Easy for me to say. And oh, hey, look. 2 steps again, and hey, look, 2 steps again, right? So that is that. The rest of these you do need to finish, of course. We have a bunch of free responses to practice, but that's why we have a few days to do it. Your goal today, though, is to tackle the Euler's method problems. We want to really cement that into your mind. Now, I mentioned, and we'll start with this free response here, that I love this free response problem. I think that's so clever the way that they ask you to do many different approximations that you've learned over the last 2 years. So let's just take a look through them first, and you can bask in the awe that is this problem. So A asks you to write a tangent line at 1, and then use that to approximate 1.4. B says, we want you to use a midpoint Riemann sum to approximate this and find the value of f of 1.4. C wants you to use Euler's method to approximate 1.4, and D wants you to write a Taylor polynomial to approximate f of 1.4. 4 different methods all to do the same thing. So let's try Euler's method to make sure we're comfortable with this. 2 steps of equal size, so I'll split this in 2. Okay. We have an initial point, 1 comma something. They better give this to us, 1 comma what? 1 comma 15. Awesome. Okay. Ultimately, we are trying to approximate f of 1.4. So f of 1.4 is going to be approximated while we have our initial tangent line and our first tangent line. So f of 1.4 will be approximated by the tangent line that's here. Okay. Well, how large are the steps? Again, I like to just sketch a nice little graph over here. We're starting at 1, we're ending up at 1.4, and at 1.4, right? And they said 2 steps of equal size. So here's 1 step in a second. I think that has to be 1.2. So we start at the point 1 comma 15, that's somewhere up here, and then we're going to get to 1.2. So this is 1.2 comma something, and then we'll use that tangent line to approximate f of 1.4. 2 tangent lines, right, to get us over there? All right, let's begin. Initial tangent line is going to use the derivative. They just called it f prime of x here, so we're going to have to find f prime of 1 times x minus 1 plus 15. And I think they do us a solid, and they tell us what f prime of 1 is. F prime of 1 is 8. Very exciting. Okay, now we have a tangent line. We move on to the next problem. The next problem, we need to write a tangent line, so f prime of 1.2 times x minus 1.2 plus, we're not going to know f of 1.2, right? We don't know this point here. This is a new y value that's not given to us. That's where the other equation comes in. So we are going to have to use our tangent line to approximate f of 1.2. You could even show it like this if you'd like. F of 1.2, which is supposed to be here, is going to be approximated by our tangent of 1.2. Is this calculator active? No, it's question 4. So we have to do a little decimal math here, gasp, but I think we'll be okay. 1.2 minus 1 is 0.2. 0.2 is the same thing as 1/5. Okay, plus 15. This does not seem great, does it? Let's, instead of doing 1/5, let's make it 0.2, because 8 times 0.2 is 1.6, and 1.6 plus 15 is 16.6. There we go. I like that better. Okay, so we end up finding that this is approximately 16.6. And cleaning up this tangent line a little bit, f prime of 1.2 is given to us. That's 12 times x minus 1.2 plus 16.6. And then we get to be efficient here, which is the nice way of saying lazy. So when I want to find the approximation at 1.4, I'm just going to take this tangent line right here and say it's 12 times x, nope, not x, times 1.4 minus 1.2 plus 16.6, and I'm done. Sure, you can simplify it if you have the time. 0.2, right, and go 2.4 and add that together. It actually comes out nicely, doesn't it? It comes out to be 19, I think. But in terms of efficiency and in terms of making sure you don't make an arithmetic mistake, just stop there. Now, I'm not going to do any more Euler's method problems. If you want, you can check the solutions online. These are all released questions. You can see how you did. They are going to show different methods for Euler's method. I'm a big fan of just doing multiple tangent lines. It's easy to see the pattern. Other teachers will teach a cool tabular or table method where you go through and you just have to remember what to multiply by what else. To me, that's extra memorization. It is a cool method, and maybe one year I'll update it, but for the frequency that Euler's method comes up, which is very rarely. It will come up once a year, but just once. I don't see having to memorize an entire new method. Just use tangent lines. Okay, so we will do one more of these, and the only other one I wanted to do was this cool one where there was a k value here. I think it's a nice little challenge, and then you guys are on task or on tap for the rest of these. Okay, so let y equals g of x be another solution to a differential equation with an initial condition 0, k is a constant, Euler's method starting at 0 with a step size of 1. That means we only do one tangent line. Well, that's exciting. Okay, so I don't even need that t of 0 thing. Now, how does this work? Well, they gave us an initial condition 0, k. Looking at the rest of the problem, we do have this differential equation. I think we'll need that at some point. 3x, 2y, and 1. So I'm going to write that over here. 3x plus 2y plus 1, and make sure I didn't transcribe that poorly. No, that looks good. Okay, Euler's method starting at 0, step size of 1, gives an approximation of g of 1 equals 0. Okay, let's perform Euler's method on this. There's only one step, so it's one tangent line, and at the end, 1 better give us an output of 0. So our tangent line is going to be dy dx, the slope evaluated at 0, k, times x minus 0 plus k. I'm going to work to the right here just so I don't run out of room. 0, k. Well, I'll just take this whole thing and use that as the slope then. So that's going to be equal to, let's see, 3 times 0 plus 2 times k plus 1 times x minus 0 is just x plus k. And cleaning this up even a little bit further, I see 2k plus 1 times x plus k. There's my tangent line. Sure, we could clean it up further, but I don't want to. And they said we used this tangent line to approximate g of 1. All right, so g of 1 was approximated by my tangent line at 1, and that answer was 0. Right? They told us the answer was 0 here. So what does that mean? Well, t of 1 is going to be found by taking this 2k plus 1, replacing the x with 1, plus k, and setting that equal to 0. Finishing the solution, it looks like we have 2k plus 1 times 1 is just itself, plus k equals 0. I'm looking at 3k equals negative 1, and so k equals negative 1/3. Just a clever way to do it, giving you a variable here. I've seen others that have a step size of 2 and things get really complicated, but I didn't feel like throwing that on here. There's already enough practice, and really you're just going to need a basic Euler's method to be successful. So please go through, work these out over the next couple days, right? What do we have? 1, 2, 3, 4, 5, 6 free responses. So if we're assuming each free response takes 15 minutes, we're looking for 2 45-minute days to get through the rest of this. And we've already done some of them. So thank you for your time. I'm excited to have you back for our next class, which is our last little topic of study within topic 5, and that will be on logistic differential equations.